Okay, so now let's talk about the mechanical properties of our polymer network. And so this will start our description of rubber elasticity. And again, what our goal is by the end of this video is to be able to predict for a given polymer network with a certain structure to it. And we'll be specific about what we mean by the structure. What is its tendency to resist changes in shape due to deformation? So we're not going to change the volume. We're only going to change the shape of the material. We're going to see what is that tendency to resist this. And as we saw in the previous video about the floor reconstruction, that tendency to resist the deformation for polymers is due primarily to entropy. And so let's maybe describe what our assumptions are right now. So our assumptions for this theory is that there's going to be no change in the volume. We're only going to change the shape of the material. There's going to be no solvent here. Okay, so no solvent. We'll talk about solvent and gels in the next video. And we're going to assume that all of the polymers are the same type, and so there's no excluded volume or no excluded volume interactions. And so as a result, the Flory exponent will be 1/2, which is another way of saying that all of the chains will behave ideally. Okay, so those are what we're working with. And so what we want to do is we want to describe, again, how these polymers are resisting changes to their shape. And the first thing is that what is the shape of a polymer? Now, if we've got a polymer chain like this, just kind of hanging out, not in a network, then we've got some ways that we can quantify its size and shape. And for us, one of the greatest ones is what is the mean squared end-to-end distance of the chains in there. Of course, mean squared doesn't make sense in this context for this static polymer chain. But how do we describe that? And the way to do it is you think back to when we described the ideal chain model, the Gaussian chain model. What we're really asking ourselves is what is the size of the chain as a result of this random walk that occurs as monomers take on different positions, and we've got different bond angles between the segments as we build up the chain from a position R0 all the way to its endpoint, which is R sub n. And one of the key things that we came up with when we did this was that the probability in 3 dimensions of a polymer chain having a size R, if it's got n statistical segments in it, this probability is proportional to the exponential of minus r squared over nb squared. And if you remember, if we were to plot that function, right, this probability, this P3D versus R, if this is 0, then we get a shape, kind of sort of like that for it. And as we increase n, then that shape kind of squats down and spreads out a little bit. And so this is a Gaussian distribution. And that's why we call them Gaussian polymer chains. Okay, so that's the first bit of information that we have. So this is telling us what is the probability to start at R0 and go to R sub n in n steps such that we obtain size of the chain R, is what that's telling us. Okay, and the way that we got this was by looking at the entropy. First of all, I should say before we talk about the entropy that this shape results for a polymer chain that's very, very large. So we've got a huge number of segments. And then, in the central limit theorem, we end up with that Gaussian distribution. So we've got to have a lot of segments here. So we should say, that n is very, very large here. So that's the first thing. And now, how did we get this probability function? Well, what we did is we were trying to compute the entropy of a polymer chain that has a size R with n segments in it. And we know that this is equal to Kb times the natural log of the number of microstates that give you a size of your polymer chain equal to R if it's got n segments. And so that's how we derived it. And we said that the number of microstates that a polymer chain has, if it's got a size R with n segments, is equal to some constant times the probability in 3D that the polymer chain has a size R with n segments. Okay, so then we took this, we fed it into our expression for entropy, we took the natural log, we simplified and everything, and what we ended up with was that the entropy of a polymer chain, an ideal Gaussian polymer chain, with size r and n segments, is equal to minus 3/2 kb multiplied by r squared over nb squared. And then because of that constant k out front, we ended up with some constant term that does not depend on the size of the chain. It only depends on the number of segments. And since we're typically interested in calculating delta S, right, the change in entropy and going from one size to another upon deformation, this constant term right here tends to cancel out. So I'm going to leave it out for the remainder of this video, but recognize that it is there until I start to take differences between the entropy to get delta S. And at the same time, we know that the free energy of a polymer chain with size r and n segments, because we're not looking at the energetic term in this case, it's really, well, maybe I'll hold off on saying that right now. If we're just looking at the free energy, let's start there. We've got the free energy of a polymer chain that has, or that does not depend on the size of the chain, but only on the number of segments. And then T times the entropy of the polymer chain that has size R and n segments. It's kind of a weird way to put it because this constant ends up being grouped in there, so my notation's a little weird. But the TLDR of that is that we get plus 3/2 kBT r squared over nb squared. Just like we used when we looked at Flory's theory for a polymer chain and a good solvent or a poor solvent, this is due entirely to entropy in this case. Of course, yeah, I've got that plus f of 0 and n. And like I said, we're typically interested in delta f, so changes in the free energy. And so that term is going to go away at the end of the day when we start computing differences because the size of the chain may change, but that term doesn't depend on the size of the chain. One thing to notice before we even start is that the free energy is quadratic in R. And so that, it's got this shape, it's almost like a harmonic potential. And so there's a certain size of the chain that's preferred thermodynamically. And as a result, the force that the chain exerts looks something like minus K, let's say delta R, if you want. In other words, what we get is Hooke's law. Okay, so just by looking at the entropy of our polymer chains, using mathematically what we know about how to handle these functions, we get that the force is linear with respect to the amount of deformation in the polymer chain. We get Hooke's law, and then again, for our polymer chains, this comes purely from entropy. So this is why I think the harmonic potential and simple harmonic motion are such fundamentally important concepts to physics, no matter if you're in polymer physics or quantum physics, or it doesn't matter. It's such an important concept. Okay. So now let's use this to describe our network. Let's look within the network first. Okay, so within the network, how does this thing look? If you remember, we've got junctions, and so here's our junctions, and let's draw 4 polymers coming off that junction. And again, these are going to connect to the rest of the network. Let's assume that all chains are elastically active. Okay, so that's the first thing. The second thing that we'll need to assume is that the junctions are static. So when we pull on the network, the junctions are going to get farther apart, but they're going to stay fixed. Imagine there's like this fake plastic sheet behind the material, and the junctions are tied to it. So in other words, they're not fluctuating. They're not fluctuating in terms of their positions. And by not allowing them to fluctuate in terms of their positions, we're actually going to overestimate the modulus of the material as compared to a real material. That's okay, right? This is our first kind of introduction to this. And so we'll say that the junctions do not experience fluctuations. You can follow it up and consider the effect of fluctuations. That's called the phantom network model, but we're not going to do it in this video. Okay, so we've got those. We've got some definitions. So first we've got the junction or the crosslink here that has a certain functionality to it. What else do we have? Well, each of these little regions, let's change colors. So each of these pieces of polymer chain that are between junctions, these are going to be called strands. They're going to have a certain molecular weight. There's going to be a certain number of Kuhn segments that comprise them. They're going to have a certain Kuhn length or statistical segment size. And the size of the gel is really going to be related to the size of the strand. And so the size of the strand, R sub S, is really related to the mesh size of the network, which I'll draw in a second. And what we're saying is that this is approximately B times N sub S to the 1/2 power. In other words, it's behaving ideally. And what I mean by mesh size is if you consider this thing, again, taking the Canadian definition, right? This looks like a hockey net, ignoring defects and things like that. If I was to zoom in on the structure of the network, you know, I might have, here's one polymer chain going to a junction. I'm going to make it square to make it a little easier to see. This goes to another junction. We've got another polymer chain that's wiggling here and goes to this junction. And then another one here going to that junction. So let's maybe color in the junctions. All right. And so what I'm calling the mesh size of the network, actually, I'm calling it something, you know, maybe something like that. Right? And you can see that it looks like it's close to the size of the strand. And so that's where we're starting. And remember that this right here is because they're Gaussian. Or in other words, the excluded volume is equal to 0. Okay, so that's our starting point. And let's make sure I didn't miss anything. Strands are the sections between crosslinks. We know how to describe them. The only other thing is that we're going to have a crosslink density. For this material, there's going to be a certain number of crosslinks per volume that's going to be there. I apologize for the notation. This is Greek letter nu. I'm going to put a little X down there for crosslink, just so that we're consistent with a lot of the notation in the textbooks that we're using in this course. But, you know, this is the number of crosslinks that I've got in the volume of the sample. Okay, and so this is going to be uniform throughout the material. And really, that's going to keep our material isotropic. Okay, so it's going to behave the same way in all the spatial directions, in X, Y, and in the Z direction. Okay, so that's a starting point for the material. That's what it looks like at the microscopic level. And now what does it look like at the macroscopic level? Well, here's my depiction of the macroscopic material. Okay, so let's imagine that we start with this square cubic chunk of material like this. Let's say that this is LX0. Okay, so that's the size of the material in that direction. Let's say that this is in this direction Ly0, and we'll call this Lz0. What we're going to do is we're going to pull on it. So we're going to deform it. And let's just say we pull uniaxially, right? So it's going to get longer in one direction, okay? And it's going to get thinner in the other directions. That's characterized by something called Poisson's ratio. And so here's maybe what our material looks like. Again, really exaggerating the changes in shape that we observe. Okay, so it's going to turn into something like this, running into space. And so as a result, now we've got a new size of our material, right? We've got Lx. And we're going to say that is going to be equal to lambda x times Lx0. In other words, there's going to be some elongation factor, lambda, that's going to describe how much we've extended it. So lambda is going to be unitless. So if we increase the length of our system by 3 in the x direction, then, you know, lambda would be equal to 3. Similarly, in this direction, we're going to have lambda y, Ly0, and that will be equal to Ly. And same thing here, right? We've got Lz will be lambda z Lz0. Right, so just a quick definition then. For example, lambda x is going to be Lx divided by its original length in that direction. Lambda y will be Ly divided by its original length. lambda z, same thing, Lz divided by the original length. Okay, so we have all of those. And what we're going to assume is that this is an affine transformation. What do I mean by affine transformation? It means that as the material is deformed in the way that I'm showing here, the polymer chains are going to deform in the same amount. So if I was to look inside this polymer network, maybe initially I've got something that looks like this for that mesh structure. And after I deform it, what's going to happen is it's going to look a little bit, you know, kind of sort of like this. It's going to exactly mimic at the micro scale what happened at the macro scale. And so let's call this, for example, you know, just to give you an idea, maybe this was R0. And now after we stretch it, we're going to have a size R. Okay. So we've got all these different things, but you know, the key thing is just like I'm showing here, we're going to describe the deformation by these elongation factors. And what happens at the macro scale is going to exactly mimic what's happening at the micro scale, or the molecular scale. Okay, so before, what do we have? Well, we've got a certain size for our strands. So we've got R0 squared would be Rx0 squared plus Ry0 squared plus Rz0 squared. And then after the deformation, right? So after the deformation, we've got the size R squared, which is Rx squared plus Ry squared plus Rz squared, right? Just for one polymer chain. So when we're doing this, you know, I'm describing maybe what's happening right here. Okay, that's how the size of the chain is changing after this deformation. Okay, so again, before the deformation, we can write the entropy of this strand. So this single strand has an entropy S0, which is a function of a chain that has R0 and N segments. And then again, we deform it after the deformation. This polymer chain has an entropy S of R and N, same number of segments. And now if we just plug in what we know for the entropy of an ideal Gaussian polymer chain, this would be minus 3/2 kb R squared over NB squared is that entropy. And before the deformation, this is minus 3/2 kb R0 squared divided by NB squared. And what our goal is, what we would like to do next is we would like to take these two things. Okay, so we'd like to take these two expressions for the entropy and we'd like to form delta S, let's say for the strand, upon stretching it, right? And going from R0 to R, we want the change in entropy of that process, which would be the entropy of the strand with size R and N segments, minus its initial state, right? Minus where it started, which is S0 of R0 and N. And so we can compute these just right now. This is going to be minus 3/2 kb times R squared minus R0 squared divided by NB squared. Okay, again, this is for only one strand, only one strand. So the first thing to do is let's just see what this is going to come out to be. We're going to expand R squared and R0 squared, just like we did up here. And again, we're going to maintain that affine deformation assumption, and let's see what we get. So delta S for the strand is going to be, let's pull out everything we don't need, right? So we've got minus 3 kb over 2 NB squared multiplied by R squared. So I've got Rx squared plus Ry squared plus Rz squared. And then subtracting from that minus Rx0 squared plus Ry0 squared plus Rz0 squared. And now Rx, squared is going to be lambda x squared times Rx0 squared, right? That's what the elongation factor is telling us along with the affine deformation assumption. Ry squared is going to be lambda y squared, Ry0 squared, and Rz squared is equal to lambda z squared, Rz0 squared. Okay, and again, this comes from the affine deformation assumption. What is happening at the nanoscale is the same thing as what's happening overall to the material. Okay, and so we're going to simplify these, and I'm going to just write down what it is. So you have to do a little bit of algebra, substitute in group terms. And what we end up with is that the change in the entropy of one strand of the network is minus 3 kb over 2nb squared, multiplied by, after we group the terms, we get lambda x squared minus 1, Rx0 squared, plus, and then the same thing for the other directions, lambda y squared minus 1, Ry0 squared, plus lambda z squared minus 1, Rz0 squared. Okay, and again, I want to really emphasize this. This is for one strand. But we have a lot of strands in the network, right? We've got on order n of them. And so what we really need to do is for the entire material, for the entire network, we need to add up the contributions of all of the strands, okay? So for the entire network, the change in entropy of the network, delta S network, is going to be, well, we're going to have the same term out front, so we're going to have still 3 kb over 2nb squared. And we're going to assume that all of the strands are deforming in exactly the same way. So lambda x is going to be the same for all the strands, lambda y is going to be the same for all the strands, lambda z is going to be the same for all the strands. So we're going to get something that looks like lambda x squared minus 1, and then we have to sum up from I equals 1 to n, Rx0, comma I squared. We're summing up all of the strands in the x direction. Then we're going to get lambda y squared minus 1. We have to sum up all of the strands in the y direction. And then the same thing for z, lambda z squared minus 1. Summation, I goes from 1 to n of Rz0, comma I squared. And now this is for everybody. And the problem is, what are we going to do with those silly sums? Right? We have to add up everybody. But remember, if we take a measurement, for example, of a polymer chain, we end up measuring the average of all of the chains in the sample, right? We get this ensemble average of all of them. If we were to do light scattering or neutron scattering or whatever it is that we're doing to get the size of it. And so at the end of the day, what we've got is, for our polymers, we usually measure the mean squared end-to-end distance, or the mean squared radius of gyration. And this is just 1 over the number of chains that we have times the summation over all of the chains of Ri squared. Now, because the chains are isotropic, because the material is isotropic, we could also say that, for example, Rx0 squared, the size of the chain, the mean squared size of the chain in the x direction, would be the average, right, of all of those values of Rx0. Same thing for y, right? So Ry0 squared would be 1 over n, and we sum up the values for all of the chains in the network. Let's just do the other one, right? Let's write down Rz squared. Again, 1 over n, summation over I of Rz0 I squared. I goes from 1 to n. And so what these things allow us to do, again, these are the definitions of the ensemble averages, right? The average of that value across the ensemble of polymers that make up the material. And so this summation that appears right up here, right, that summation, for example, we can write in terms of these definitions of what the mean squared values are. So for example, the summation as I goes from 1 to n of Rx0 I squared is equal to n times the mean squared value, right? The summation as I goes from 1 to n of Ry0 I squared is equal to n, again, times the mean squared value. And why not? Let's just do it for z too. Right? The summation of Rz0 I squared is, again, n times the mean squared value across the material. So now we can just substitute in for those values. We've got n, we have the Ry0s, Rx0s, all that stuff. One other thing, we saw last semester that if we wanted to compute, for example, Rx0 squared, this was actually a homework problem, we can evaluate that by integrating from minus infinity to infinity of Rx0 squared. Since we're only looking in one dimension, though, this would be multiplied by the probability in 1D of a polymer chain having a size Rx0 n drx0. So we integrate across all possible values of Rx0. We put the thing in there that we're interested in. We multiply it by the probability function. Again, this is in one dimension. And on the homework, you saw that this was equal to nb squared over 3. Because the chain's isotropic, this is 1/3 of its value. And so with all of this, this allows us to simplify our expression. So therefore, the change in entropy of our network, which is giving the mechanical response, is going to be, when we add everything up, minus 3 kb over 2nb squared, multiplied by, we've got lambda x squared minus 1, multiplied by n over 3. And then we've got, what? Rx0 squared, divided by 3 is the 3 that I just wrote. So this is multiplied by nb squared. Okay, so I'm just substituting the terms in. Plus lambda y squared minus 1, multiplied by n divided by 3, nb squared. Hopefully you see what's happening here. I've got all these terms, and they're going to start canceling out. And then finally, lambda z squared minus 1, n over 3, nb squared. And now let's see what cancels, right? So what's going to cancel here? Nb squared is going to cancel nb squared, nb squared, nb squared. 3 is going to cancel 3, and 3, and 3. And I think that is it for now. And so what we end up with, once we look at all of these things, we get minus, n is common to all the terms, kb over 2. We take all the lambdas, we combine them. We take all the ones, the minus ones that are there, and we combine them, and we get lambda x squared plus lambda y squared plus lambda z squared minus 3. So if you tell me how much you've stretched the material in the x, the y, and the z directions in terms of these elongation factors, lambda, then I can tell you how much the entropy of your material has changed. That's what we've just computed. Okay, and so that's delta S for the network, and so delta F for the network. Remember, that constant term in the free energy is going to cancel. That F of 0 and n is going to cancel when we subtract the two things. And so we're going to end up with minus T delta S of the network. So the minus sign is going to go away, and what we're going to be left with is N kBT, our thermal energy, divided by 2, multiplied by lambda x squared plus lambda y squared, lambda z squared minus 3. So nice. We've got both the entropy and the free energy changes of our network, as a result of what happened in lambda x, lambda y, lambda z. So the other thing is, remember, we've got this condition for our material. One of our assumptions is that dV is equal to 0. So V0 is going to have to be equal to V final, right? So that means that Lx0, Ly0, Lz0, the initial volume, must be equal to lambda x, Lx0, lambda y, Ly0, lambda z, Lz0. Again, only if, right? Only if the volume of a material does not change, which is true. This is an incompressible system. Our polymers are incompressible. The volume's going to be the same before and after, at least in what we're describing here. We'll talk about experiments in a second. So that means then that lambda x, lambda y, lambda z must be equal to 1. And this is going to be the constraint we're going to use for our material. Now, I will say in real life, there are small changes in volume. Okay, so just keep that in mind. But they're small, okay? So they're not really affecting what we're talking about here. And so the very last thing to do in this video is we want to look at the case of uniaxial deformation. So we want to look at deformation in one direction. So uniaxial deformation of an unentangled network. So think back to the Flory construction video. Unentangled means we're not going to have those crossings of the polymer chains that act as physical crosslinks. We're going to add those in after we do this. So what we're saying is we're going to take our material and we're going to elongate it in one direction. So we're going to pull with a force in the x direction, or really what we're interested in, right, to make it more general, is we're interested in the normal stress that we're applying in the x direction. Notice that that means that this material is going to get longer in the x direction by a factor lambda. But as you saw with the rubber band, in fact, let's just look at it again. Here's the initial thickness of the rubber band. When I pull on it, notice it gets thinner in the other directions. And so while it gets longer by lambda in the x direction, it's going to get thinner in that direction, okay? So that's how our polymer is going to behave. And we know that lambda multiplied, in this case, let's say this was like lambda y, okay? So lambda is going to be bigger than 1, but lambda y and lambda z are going to be smaller than 1. Lambda times lambda y times lambda z must be equal to 1. And because the material is isotropic, the amount that the material is going to shrink in the y and the z directions should be the same, or we're going to assume that they're the same. So this means that lambda multiplied by, I don't know, let's call it lambda y squared, must be equal to 1. So lambda y is going to be 1 over the square root of lambda, and that's going to be lambda z. Okay, and again, this is because we're pulling in one direction, and because our material is incompressible, its volume is not changing. So what we want to do is we want to take these things, we want to substitute these, maybe not that one. We want to substitute these along with lambda x equals lambda, substitute into our expression for the free energy, and see if we can model, again, the mechanical response of our material and how much it's resisting that deformation in the one direction. So the change in free energy for our network upon being stretched, right? What we just did, we said this is n kBt divided by 2. Now if we substitute in lambda x and lambda y, we're going to have lambda squared plus 1 over lambda plus 1 over lambda minus 3. So we get what? N kBt divided by 2 multiplied by lambda squared plus 2 over lambda minus 3. Okay, and again, this is uniaxial only. And again, this is under the assumption that dV is equal to 0. And now, again, we're trying to see how much our material is resisting this deformation. So we really want to see how much force it's pulling back with. And so the force in the x direction is going to be the derivative of delta F for the network with respect to L in the x direction. And we know that Lx is equal to lambda x times Lx0, and Lx0 is a constant, right? That's the initial length in the x direction. So this is the same thing as 1 over Lx0 times the derivative of delta F network with respect to L, oh, sorry, not L x0, but with respect to lambda. All right, and that will give us n kBt divided by 2 Lx0. And nope, the 2 went away when we took the derivative. All right, and that will be multiplied by, again, we took the derivative of what's in the parentheses with respect to lambda. We get lambda and then minus 1 over lambda squared. So again, when I deform my network, that is the magnitude of the force that the material is pulling back with in the opposite direction of the stress or the force that I'm applying in this direction. And because everything's in equilibrium, those forces must be balanced. All right, and so that's the force, but that's really specific to this material. What would be better is the stress, right? So that we can do this for any dimension of material. And so the stress in the x direction, that normal stress, is going to be the force in the x direction divided by the cross-sectional area, which is Ly Lz. So this is going to be equal to n kBt divided by Lx0 Ly Lz, and again multiplied by lambda minus 1 over lambda squared. And for these things here, right, we know how those are related to their initial dimensions by those elongation factors. So we can substitute in. So for example, Ly is going to be Ly0 divided by the square root of lambda. And that will be, well, that's just in the y direction, right? And so we can also say that, whatever, Lz will be Lz0 divided by the square root of lambda. And so those two square roots are going to pull up a factor of lambda into the numerator. And so this is going to give us n kBt divided by volume times lambda minus 1 over lambda squared. So that's the stress. And again, V is just Lx0, Ly0, Lz0, right? And that's before, the same before and after the deformation. And so this is the true stress. Okay, so the true stress, the true normal stress in the x direction is going to be n kBt divided by volume times lambda minus 1 over lambda squared. We don't always know exactly what those dimensions are as it's in the y and the z direction as it's changing shape during the deformation. And so sometimes we define also the engineering stress. So the engineering stress, say eng, is going to be n kBt divided by volume divided by Lx0, Ly0, Lz0, which means that that factor of lambda that came up to the numerator is going to disappear. And so the true stress is going to look like lambda minus 1 over lambda, sorry, the engineering stress is going to look like this. And as you can see, that's the same thing as the true stress divided by lambda. And so now we've got an expression for what the stress is, and what we're trying to figure out is how much it's resisting. Well, this is telling us how much it's resisting. I'm pulling down with a certain force, or I'm applying a certain stress in this direction, and I know how much the material is pulling back, and I know how that's changing as a function of the elongation. And actually, if you look at this expression right here, I've got two things that are going on. I have this prefactor out front. This is a material property. Right? I've got the number of crosslinks per unit volume multiplied by kBt. Number of crosslinks per unit volume, that has to do with the structure of the material. That is a material property. But over here, I only have lambda, And this is telling me only about the deformation. And so what I've ended up with by doing this is I have some expression where the, let's say, stress is equal to some constant. Notice that this prefactor is the same for both the true stress and the engineering stress, right? So that's a material property. We'll call this G, our shear modulus, and we'll multiply this by lambda minus 1 over lambda squared. Okay, so that's our material property. And you can see that the material property G, again, this is our shear modulus. Because we're only changing the shape of the material, because the volume's holding fixed, this is actually the only independent modulus of our material, right? In the case that it's incompressible. And so this is equal to the number of crosslinks per unit volume times kBt, or in other words, it's equal to our crosslink density times kBt. Okay, that's fine. It's not always the most convenient way to do that. So imagine that we've got a density to our material, rho, which is the mass of our material divided by the volume. Then this means that the density of my material, so this implies that the density of my material divided by its mass is equal to 1 over the volume. And actually, if I express my material a certain way, so for example, the molecular weight of the strands, the molecular weight between crosslink, has units of grams per mole, which is different than the m in the expression above. But what this gives me is I can write this instead as, to describe my material, the density of my material times Avogadro's number divided by the molecular weight of my material between crosslinks will give me 1 over the volume of my material. And so my shear modulus then, I can write two ways. I can write it as nu x kBt, and that's the same thing as the mass density of the material multiplied by Avogadro's number multiplied by Boltzmann's constant times temperature divided by the molecular weight between crosslinks. And actually, Boltzmann's constant times Avogadro's number is just the ideal gas constant R. So this is the same thing as rho RT divided by m sub s. Okay, so we can notice a few things. First of all, the shear modulus increases with temperature. It also increases with the mass density, which is kind of telling us that we probably have more crosslinks, right? This is telling us entropy plays more of a role. And the last thing is that G decreases as m sub s increases. And this is telling us that we have fewer crosslinks, right? And we can kind of see it this way, right? If we, let's go back, let's draw these crosslink points, these junctions in red, and let's draw our polymer chains in. So I've got something like this, roughly speaking, for the structure of my network. Again, I've also got this size here, Greek letter C, that I'm calling my mesh size. Remember that the mesh size is basically B times n sub s to the 1/2 power, which is the same thing as B times m sub s divided by the Kuhn molar mass to the 1/2 power. And what this is telling me that G decreases as m sub s increases. As m sub s increases, then the mesh size gets bigger. So C increases as m sub s increases. So in other words, as that happens, if you think about it, these points here, these crosslink junctions, as m sub s increases, they kind of sort of get farther away from each other. So what that's telling me is that, again, my crosslink density, all other things being equal, right? Holding all the other values equal, my cross-link density is decreasing if I do that. And so that's the basic way to describe how this thing is resisting deformation. In the next class, I'll do some examples of computing these different quantities, so computing G and kind of estimating the structure of the network. But for now, let's just consider one more thing, which is, what about entanglements? Right, so what happens when these chains are crossing over each other and restricting their motion? So I've got a polymer like this, and then I have another one coming in next to it, and it crosses maybe over here, and then under here, and then over here, and under here, maybe under there, and over here. So in this case, I've got a certain number of physical crosslinks that have formed in my sample, right? I've got a crosslink here, 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 and here. And on average, right, on average, I have a certain molecular weight between entanglements, okay? So I've got a certain what we call entanglement molecular weight. And so if you think about it, this whole theory up here of what the modulus looks like, it should kind of mimic what happens with the entanglements, right? It doesn't matter if they're chemical or not. What matters is how many crosslinks I have, or equivalently, how big the junction or the sections of chains are, the strands are between those junctions. And so my overall modulus for my material, when I take this into account, the total modulus is equal to G of the network, the shear modulus of the network, plus G due to entanglements. And so what I get at the end of the day is rho RT. I do get that, but I want to write it a little more neatly. I get rho RT multiplied by 1 over the molecular weight of the strands, the molecular weight between, let's say, the chemical crosslinks, plus 1 over the entanglement molecular weight. So again, this is due to, let's say, the crosslinks, the chemical or whatever crosslinks. This one here is due to entanglements. And this is really fixed. For a given chemistry of polymer, this entanglement molecular weight is fixed. And so this is the only thing really that can change. And in an upcoming class, we're going to talk about entanglements and what that does to the dynamics of a material. But for now, I want you to think of these entanglements as being fixed, these crosslinks as being the thing that we can change by changing the network structure. And because of this, you can see that if M sub S got really large, right? If we made it really large, in other words, we made the crosslink density really, really small, then the shear modulus of our network, right? We're just going to call this G. The shear modulus of our network is going to approach rho RT divided by M sub E. So entanglements place a fundamental limit on how soft you can make your material. Then the question is, well, how do you get rid of the entanglements? How do you start making them play a different role? And one of the answers to that question is you start changing the molecular architecture. So we'll talk about that in an upcoming video. We'll talk more about entanglements and entangled dynamics in an upcoming video. But for right now, this is how we describe, G describes the resistance of our polymer network to shape changes. And now in the next class, what we're going to do is we're going to take this information that we have, this understanding of polymer networks, and we say, okay, well, what is the effect of adding solvent to the network? And I'll see you there.